So welcome to the Stats for the Masses webinar. It's a Meta U Betta overview of systematic reviews and meta-analysis. My name is Elaine Eisenbeisz. I'm the owner and principal statistician here at Omega Statistics. Today I'm going to present a quick review of systematic reviews and meta-analysis. I'm going to show a real simple example also in MedCalc. So it's a software called MedCalc. Today is just an overview. There's no way I can cover the whole of systematic reviews and meta-analysis in an hour or so. But as always, I hope that the information you receive today will give you some ideas and guidance towards further research into these techniques. And as I say in all of the webinars, use what you learned today and apply it in a holistic way. So look at the big picture. One of the things I can say about this topic is that it can be very subjective. So we'll be talking quite a bit about bias today also. I scheduled a total 90 minutes for the presentation and the questions. So let's go ahead and get started with our slides. Those of you who know about the company and what I do know, and those of you who don't, you can read through this slide and see kind of what Omega Statistics is all about. I am a private practice statistician. I work in Southern California. I help mostly with dissertations and clinical trials, clinical research. But I basically, being a private practice, I help with just about any kind of stats. I do also offer seminars and webinars. I offer these free webinars quarterly. And if you go to the Omega Statistics website, you can see some of the fee-based offerings I have. And our motto is to provide elegant solutions effectively applied. So here's some things that we're going to cover today. First of all, why perform a systematic review or a meta-analysis? We'll see a little bit of history and reasoning for the systematic reviews and meta-analysis, some terminologies, we go through things, right? And I'll show you some of the steps in performing a systematic review and some steps in performing a meta-analysis. And like I said, it's the basic stuff today, but you know, hopefully you'll learn a lot. It'll be a good base to move forward and learn some more. I'll give you lots of references. Okay, so here's our quote for today. Knowledge is power. They think that probably came from Francis Bacon. It's been around a long time. It's Latin, so you know, somebody might have said it before him. But then that's kind of what meta-analysis is about. You know, it's about synthesizing a lot of knowledge together. Okay, so we also have Francis Bacon to thank for the scientific method, along with some help he had from Copernicus and Galileo. Okay, so here's some definitions. Collecting and summarizing all empirical evidence that fits a pre-specified eligibility criteria. That is a systematic review. So you're going to search the literature and what's out there, the empirical information, and kind of synthesize it all together. Typically, we do it to get us an effect size or some kind of overall look at the literature that's out there, the evidence that's out there. And then a meta-analysis is statistical methods that we use to summarize these results of the eligible collected studies, and it's part of the quantitative systematic review. A systematic review does not always lead to meta-analysis, and there are other types of review. A review of the literature is a meta-analysis only if it includes some kind of quantitative estimation of the magnitude of the effect and the uncertainty. There's a variability around it, the error around it, right? So, and there are other types of reviews. There's narrative reviews that are like critical analysis or a literature review, and there's also qualitative systematic reviews without the numerical data. But today we're going to be using the combination of the systematic review with the meta-analysis. Here's some history and background. Carl Pearson appears to have been the first to kind of analyze clinical trial results using meta-analysis, and he suggested that experimental designs would be the best kind in a meta-analysis. And an experimental design is when you randomize into groups, you randomize your people into groups, and you have a treatment that you do to one group, and you maybe have a control or a placebo group. You could have more than two groups, but it's basically you want to randomize and then give a treatment to some and treatment to not others and see what comes from that. See if you have a treatment effect. Randomizing is supposed to control for any other kind of what we call latent effects, effects that you can't see but they're there, that you're not including in your analysis. So if you that's why we like randomization. But he did a study of the effects of typhoid inoculation, and he did a study on those who had volunteered versus those who hadn't volunteered to be inoculated. So they weren't randomized. So he did come up with his results and such, but he did think a little bit further, and he said that, assuming that the inoculation is not more than a temporary inconvenience, right, it would seem to be possible to call for volunteers and only to inoculate every second volunteer, say, with a view to ascertaining whether any inoculation is likely to prove useful. So in other words, the experiment might demonstrate that inoculation to be effective, and it's not a false kind of finding. Okay. Ronald Fisher, in 1944, he started the idea of accumulating probability values, and basically it's when a number of quite independent tests of significance have been made, it sometimes happens that although few or none can be claimed individually as significant, the aggregate gives an impression that the probabilities are on the whole lower than would have been obtained by chance. So what he's saying is that more or less one test and one study is never conclusive. I think it was Einstein that said, one study could, prove me wrong. Even though the study I did was, it seemed to prove, no study can prove me right, but somebody can come along and prove me wrong. They can just find the results that are different. Right. And so one study doesn't really hold up. And that's why we do studies over and over again and have this repeatability, and we want that reproducibility. So Fisher was kind of onto that, and Pierce was onto the experimental design. And in Cochrane is what you'll hear a lot. There's the Cochrane Review and the Cochrane Library, and he was very, very big on randomized controlled trials. And those are the ones where you randomize into groups and then do the treatment on one or more, but you always have that control. So he was saying that he might like to use some observational studies where you're not going to randomize, where basically it was like the volunteers, or maybe just everybody at one point in time, and you're just looking at them, something more observational and not experimental. And he was doing some studies, and he said that he could come across a number of comparisons that were well done but not randomized, and that he would have been interested in including the observational studies to learn whether they agreed with the randomized studies, and if not, why not? But he said the medical members of our team had been too well brought up by statisticians and refused to look at anything but randomized experiments. And you will find that as we go through things, the randomized control study, besides the meta-analysis itself, the next level in the best kind of studies are randomized controlled trial. Those are what we like. Meta-analysis did get its name from Gene Glass. He coined a term in 1976. Others, of course, have contributed to systematic review and analysis of the information. It is kind of interesting how it came about. In 1952, there was a researcher, Eisenbeisz, I think is how you pronounce the name. He concluded that there were no favorable effects of psychotherapy. So it started like this great big raging debate for 20 years of research and hundreds of studies. They failed to resolve the debate. Things were still inconclusive as to whether or not psychotherapy was working. So Gene Glass came along and statistically aggregated 375 psychotherapy outcome studies with his colleague Smith, and then they concluded that psychotherapy did indeed work. It did have a treatment effect, and he called his method meta-analysis. And meta means referring to itself, like self-referential. So in the case of meta-analysis, it's a review of reviews. So try to think of it that way. But it's pretty fascinating how it comes about, how sometimes things come about in research. Another great thing with the history and background is one of the earliest studies was a synthesis of literature and meta-analysis to investigate whether aspirin reduced recurrences of heart attacks. Okay, and so the researchers found in a single study that there wasn't a statistically significant effect. Oh, that's too bad. They didn't find anything. However, when they combined many studies and then did the meta-analysis, there was indeed evidence of a positive effect of aspirin on preventing recurring heart attacks. So now that's a given. We just understand that as being a truth, and it's because we synthesized information together to get at that overall what the whole meant, right? Okay, so there's lots of strengths. You can read about them here. The systematic reviews can be of interventions, right? They could be like the randomized controlled trials, or observations like a case control or a cohort study, things like that. But the type of study to be included will depend on your research question. Sociology and psychology have been performing systematic reviews of observational studies for decades, and many of the recent resources that have been developed within a medical framework that are using the randomized controlled trials to assess whether a treatment is effective or not continue. Not so many observational that you'll find in health research, or you'll usually find a randomized controlled trial, but they are becoming a little more common. Because sometimes a randomized controlled trial is just not feasible or ethical. For an example, it wouldn't be possible to randomize children to poor or enriched social environments to maybe assess that impact on social intelligence. You don't want to hurt anybody while you're doing your research. So I do want to let you know that it is very difficult to perform a systematic review alone. The highest quality reviews are going to have input from experts in the subject being reviewed. So you want some people that are good with the methodology of review, some people that really know where to find that information and get it. And of course, statisticians are very useful to have. And so these strengths, it does help resolve that uncertainty when original research reviews and editorials are disagreeing. Not every study is going to come out significant, so there will be some literature that says significant, and a lot of times you won't even see non-significance in the literature. Very often, if you don't have significance in your study, it doesn't get published, and so that's a publication bias, and so we try to control for that in these meta-analysis. A lot of times studies are powered at 80%, and that means that they're allowing for a 20% type 2 error, which means false negative results, which means the significance is there, but you missed it. Okay, you didn't see it. So that's 20% of the time in most studies, you're allowing yourself to miss significance that truly is there, but you just didn't see it. You didn't collect enough data maybe, or for whatever reason. Usually it's not enough data. And then we can use them to explore treatment effects in subgroups. So maybe you have an overall effect, but now you want to look at males and females, maybe different age groups, different follow-up times. Explore and explain what we call heterogeneity. Okay, and we want our studies to be comparable, right? You want to be comparing apples to apples. Okay, so you don't want to have a lot of different studies that were done a lot of different ways and have a lot of different types of outcomes. That you want to make sure that they're, the variance and the variability and such between them is what the heterogeneity is. But it's just kind of to help you make sure that you're comparing comparable studies. We'll talk more about that in a bit. And sometimes it helps guide the direction of future studies or even develop new research questions. But I say, in my humble opinion, the biggest reason is because it provides evidence-based research and practice. That means we're taking information that's been out there, that's been published, that's been studied, hopefully from good peer-reviewed journals, really good places, and other good areas of research, and we're combining it together, and it's evidence-based, and it enhances everybody, clinicians' practices, doctors, everybody would rather have a synthesis of the literature, and I think that's the biggest reason. It really gives you an overview of what's out there and the effects as a whole from all the studies. There are some caveats. So when you're working with systematic reviews and a meta-analysis, you got to make sure the quality of information you're collecting. Studies that, even on Google Scholar, you want to be careful. Try to get it from peer-reviewed journals. And journals that are thought highly of, mostly for your journal articles and your other research, other documents, editorials, things like that. You can include a lot of different things. Most people will include journal articles. That's the big one. And of course you need to control for bias. It's a very subjective type of thing, a systematic review. which ones are we going to include, which ones are we going to exclude, and why. And so you really want to have a really good inclusion exclusion criteria and help you control some bias on that. And then there's publication bias. As I was saying before, usually only significant studies get published. Sometimes you'll get a really, really, really big study that a company or person spent a long time on and, spent years on, and they won't get significant results, and they'll still publish it just because they want to show something for their efforts. But typically, if you don't have significance, it's called what we call the file drawer fallacy. All these studies that you've done that won't get published because you didn't find significance, you throw them in your file drawer. Okay, so there's a lot of bias that you need to control for, at least be aware of. And they're most useful whenever there's a meaningful research question, and there have been several studies published, and then there's still some uncertainty about what remains. And typically, whenever I do meta-analysis, we're looking for a treatment effect, and it's usually in a randomized controlled trial, because I do work a lot in clinical research. So you have the treatment group and you have the placebo group, and you want to see if that intervention you use as the treatment, what was the effect, and so that's what a great use for a meta-analysis would be, those type of studies. Okay, here's some publication bias. So as I was saying before, studies with significant results, most studies you read have a significant result. They're more likely to be published. Okay, we have that file drawer bias when they're not significant. They're more likely to be published pretty fast, right? So you'll have less lag time. They'll publish those really quick. They're more likely to be published in English. Okay, they're also more likely to be cited in other literature. Part of the meta-analysis is you find a great study, then first thing I want to do is go to the reference section and see what other studies I can pull out of there, right, and search. So they're going to be, you'll see them more likely cited in the literature. So they're also going to be more likely to be published more than once. Sometimes the person will have a big data set and they'll use it for 20 studies, or a large type of research, would be used, or a huge database. So sometimes they'll be published more than once, and maybe even in more than one paper. So then there's outcome reporting bias. Significant outcomes are more likely to be reported, as I said, and non-significant findings are typically not reported. So those are different biases. Okay, and here's the steps in the process, and we'll go through them a bit today. So first, you're going to figure out what your problem is and your hypothesis. Make it clear, make it answerable, make it fairly simple. Okay, and then the next thing you want to do is see if it's already done. And I'll show you some ways to do that. And it's always a good idea to register the review that you plan on using. There's some places you can register it. And then you're going to perform your literature research. That's the most exhaustive part, is doing that literature research, and then your data collection and extraction, 4, 5, and 6. And your quality assessment. Those could take years, sometimes. Typically it'll take about a year to 2 years for most of these studies. So again, you'll do your analysis, and then you'll interpret, make your report, and then hopefully you'll publish your protocol and your review. Alrighty, so first thing you want to do on a systematic review, formulate your problem. Okay, and you'll see this often in health research. I work with a lot of nursing students and a lot of administrators and a lot of researchers in the health field, and they have the PICO or PICO question. And it can be used to formulate the problem. Okay, so first you have the P is for patient or person, right? Who is or who are the people you're studying? What's the group of people you're studying? Who are they? What's that person like, right? You'll have your intervention. Okay, so what's the intervention you're going to do? Or, or maybe there's a certain prognosis they have that you want to investigate and follow. Maybe there's a certain cause of some kind of condition they have that you want to follow. A comparison. So is there a standard that you're going to be comparing to? Is there a standard treatment out there already? Or are you going to compare to maybe a placebo or a sham procedure or something like that? And then, of course, your outcome. What's your outcome that you're looking for? What outcome are you investigating? So after you formulate your problem and you search the literature for, I call it doability. I couldn't think of a better word. Then you're going to define your specific research question that can be answered. So yeah, so first thing we want to, well, second thing we want to know, I guess, is has this already been done, right? So to avoid wasting your time and energy, you need to establish whether this question's already been answered in the public literature, or is it registered as an ongoing review? So you want to do search with the systematic review registries, and these registries, they contain abstracts of quality assessed systematic reviews and details of current protocols that are out there. And also consider registering your own study, okay, in a registry. So this is going to ensure that others know yours is ongoing, okay, and actually many journals now look for registration to ensure high quality reviews which don't deviate from that predefined criteria. So they kind of go back and search and go, okay, this is what you said you were going to do, so let's see if that's what you did, and it helps them assess how well your study holds up. So we have here the Cochrane Library of Systematic Reviews, the CDSR, and here's a link that you can go to. And they usually do the healthcare intervention and diagnostic studies. This is what I usually use. Okay, there's the NIHR, which is the National Institute for Health Research, and they have Prospero Registry, and that's health or social, and that's based in the UK. And then there's the Campbell collaboration, and they do the social interventions in education, crime and justice, social welfare. So there's a couple registered, 3 of them there, probably the most known, the only ones I would really think about. So as I was saying, you need your inclusion and exclusion criteria. Oh wait, I have a question here from Jerry. Oh, clinicaltrials.gov. That's right, Jerry. That's another place that's a place to register your clinical trials. And systematic reviews, I'm not sure, but I know clinical trials for sure. He said clinical trial study. So yeah, thank you, Jerry. So now our inclusion exclusion criteria. Okay. Once the problem for investigation has been formulated, we must compile a thorough list. Okay. So are we only going to include randomized control trials? I've had many clients that say, yes, I only want randomized control trials. And then you search the literature and there's just not that many that are acceptable to use. So you kind of have to expand that out a little bit. But there are quite a few areas of study where you could find enough of those, because those are the top tier things. Those are the trials you want to do, if you can. How far back are you going to search? Obviously, more recent research is going to be better, but you might want to go back a little ways. Maybe research has changed. Maybe things have changed over time. Sometimes new instruments are involved. Sometimes new technologies are involved, right? Advancements. When you really think about the medical field, as a field we know it today, it's only been around maybe 200 years or so. So we're still learning so much, right? So things change over time. What's your population of interest? Which age groups, genders, race, all your demographics, right? Where are they from? Whatever information you might need about them. Are you only going to look at peer-reviewed articles? What are the interventions? What are the outcomes, right? What interventions are you looking at, and what outcomes are you looking for? And what study designs will be considered? Again, are we only going to do the RCTs? There's many more things. You could probably think of many more things, but the one thing you need to remember is that inclusion and exclusion criteria must be agreed upon before data extraction. Otherwise, you're going to have something called selection bias. And again, that even could be where it's like, hey, I wanted all RCTs, but now, darn, I can't find enough. Have we just biased the study, right? So don't make yourself too stringent at the beginning where you're going to have to go back and change things. That doesn't look good, but also don't leave it too loosey-goosey either. So this takes a lot of thinking. And again, this is another reason why it's nice to maybe have more than one person doing these studies together. All right, so here's the hierarchy of studies, best to least. I borrowed it from this page from the National Health and Medical Research Council, had this levels of evidence. It was open source, so I went ahead and just, rather than make one, I borrowed it. If you want to go look, there's their web address. So systematic reviews are best. Oh, we like that, and I called it least best, because I mean, all these studies have their pluses and minuses, right? So I don't want to say anything's worst or bottom, right? But so I just said best to least best. So systematic reviews first, which is what we're learning today. Critically appraised topics, evidence synthesis and guidelines, right? So that's more of a kind of a systematic review thing or a critical review. Individual articles, like article synopses that are critically appraised also. These are all filtered information, meaning they come from more than one study, okay? Then we have individual study kind of things, where we have the randomized controls trial, okay? So that's where it's one trial, one study, okay? Cohort studies, and then of course case-controlled studies, case series or reports, and then of course expert opinions at the bottom, okay? Observational studies, I think I mentioned before, are often used with the systematic reviews, but the meta-analysis has been extensively applied for these randomized controlled trials, okay? And because variations assumed to be due to chance, and the meta-analysis increases precision. However, meta-analysis is used on observational data more and more lately. It's attractive to use them on observational studies because we often observe small effects and inconsistent findings. So especially the inconsistent findings make that systematic review very useful for observational studies. Another note about the observational studies is that bigger is not better. Not necessarily, sometimes. There's a danger that meta-analysis of observational data produces precise, so you get a really good bead on your treatment effect and maybe a really good tight confidence interval around it. However, they could be spurious, right? Which means that there could be something else causing what you're seeing, causing that effect instead of what an intervention or something, right? Because you didn't control and randomize, right? You observe. So when you're doing that, you really want to take a really good look at that heterogeneity concept. Okay, so statistical combination of data should not be the main component of a systematic review of observational data. It's often desirable to have individual level data for this purpose, which would be nice if you can get it. But a lot of times in trials, you don't see the individual patient data, right? So you basically do have to combine the aggregated kind of data. And then, of course, you have confounding effect modifiers. They can pose a problem with these non-experimental designs because you didn't randomize. So you're not controlling for all those confounders, okay? So those are the different hierarchies on it. Let me see if I have any questions. It looks like, nope, good. On to the next. Okay, lots of places to search. Here's a list. You can just look them all up, and it depends on where you're searching and what type of study you're doing. You know what topic you're looking at on where you're going to look. But there's some. Here's a link for more. This is a great link. It showed me ones I had no idea. Okay, and there's some videos in there, different links to different places you can look, and of course you're going to need search terms, right? So you got to go into these databases, and if you're say looking at I think today I'm just doing something silly like, oh, does wearing slippers help you to stub your toes less? Okay, so you would put in like search terms like, wearing slippers, stub toes, maybe just toes, things like that, bare feet, things like that. And you want to make certain to keep good notes of the databases you checked, the search terms you used, when you downloaded your articles, because you're going to need this information in your reporting. And the big thing, it also allows others to reproduce your search strategy. If people want to know how you did it and reproduce it, then they have the details. So we want to keep things neat and tidy, okay? So you're going to review the literature you've chosen. You're going to extract necessary information from each study. And I prefer to do this in Excel, and I'll show you a little skeleton file I made in a minute. And you might want to check into some reference management software. There's EndNote, RefWorks, Zotero. A lot of people seem to be liking now the Zotero. Mendeley, I don't know much about. Site You Like. Okay, I think which ones are free? I think Site You Like is free, and RefWorks, I think you can get it free. Okay, Zotero, Mendeley, and Site You Like are free, and then many universities are going to provide this RefWorks for free to students. Okay. So let me go ahead and show you what I do. I make a little skeleton file, and it's different for different studies because it really depends on what I'm doing, what I'm looking for in a study. But here's like, I just make a little Excel file. Um, this one was for a study that I did where we had a baseline and end of study measurements for both the treatment and control group. So we took measurements at baseline for the treatment and control, and then we took a measurement at the end of the study for the treatment and control. Okay, so I did have to do a special formula for the standard deviation or the variance here. Okay, so but what I'll do is I'll put the ID of the study. I'll give every study a number. So it'll be, and I'll put, if I print it out or I save it in my file as a PDF or whatever, I put the number with it. So trust me, you're going to go back and look at these studies a lot. So you want to be able to find them. Then I'll put the authors and the year. Then I'll put what they tested on their hypotheses. So this would be maybe a change in means from baseline to edit study. Okay. And then here's where I put the standardized mean difference, D, and you can get that computed. You can compute it yourself. I'm going to show you a great link in a minute where you can go and compute effect sizes. Here's the variance that I needed for the standardized mean difference. It was, since it had a before and after for both the treatment and control, I had to find a special formula. And so I just put that in there. And then, of course, the standard error of the variance is always the square root. So I just did the square root of F2 here, right? To get my variance here. And then here's some of the other important information we're going to put in. We're going to put in our the number of patients we had at baseline and the treatment, the time. Let's see, treatment effect time at time 0. Okay, so this is the mean at baseline. Okay, and here is the standard deviation at baseline time 0. Okay, and that's for my treatment groups. And then for my control groups, here's the sample size. Here's my mean for the control, and here's my variation for the control, the standard deviation for the control at time 0 baseline. And then also I have end of study, and I do the same thing. Treatment, sample size, mean, standard deviation, control, sample size, mean, standard deviation. That's basically all I'm going to need. But if I have any information I need to put in here, I'll write some little notes or comments. Okay. And a lot of this information I'll be using for the meta-analysis. But I just set up something simple like that. And then you can kind of, you just need to be able to go backtrack it. You definitely want the sample sizes and your effects for each group at each point in time. You might even want to put in this type of statistical test that was used. That's always a good idea. I have a study that I worked on recently where I had ANOVAs, I repeated measures ANOVAs, I had t-tests, but they were all kind of studying the same effects. So I had to kind of figure out a general effect size that I could use for all those studies. And it does get complicated. I'm not going to show you today. I'd probably have to go back and look it up myself, how I did it, but I did it, So, if you can get everything that's the same and it's always a mean difference, you're lucky. But a lot of times, somebody might use a correlation, somebody might use a t-test, somebody might use a chi-square, something, depending. But it's just it is what it is. So we want to assess the quality of each study, right? There's not one consensus on how to do this, but here's some ways. Cochrane collaboration, you could never go wrong with that. Here's a risk of bias assessment tool. Let's see if I can click on that and get it to go. Oh, it's not going to go. Control click. Okay, let me see if I can get it to go into a browser. I want to show this to you. And I think I put these in the references section, so you'll have them. Okay, so here's from the Cochrane collaboration. And it's just that you want to start assessing the risk of bias, right? You want to see if your study qualifies or not. Okay, so here we have the, you want to see, here's the different domains: selection bias, right? Performance bias, detection bias, attrition bias, and reporting bias. Okay, then here's the support for the judgment. This is what you're looking for. in your article, each of your articles, and then here's would be your judgment and whether or not you're going to accept it. And you can maybe give it a point for each, or decide whether or not you're going to keep your study. And I would probably put this in the notes. A lot of times I'll have another column in my worksheet that will I'll have all the literature that I reviewed in there, and then I'll have another column that's just coded 0, 1, and I'll code it 1 if I'm using a study and a meta-analysis, and 0 if I'm not. And I'll usually have a reason why. As you can see, if you look at most of these and most assessment tools that are out there, most of these relate to randomized control studies, okay? So, was there random sequence generation? Okay, was there allocation concealment? Okay, so did we randomize people into groups? Okay, allocation concealment is it's helping to avoid the selection bias. You want to make sure that you have it all double blinded, that we want to make sure that nobody can tell who is getting what before the treatment. Whether they were getting a drug or control, things like that. So it's kind of like blinding, but you want to conceal that sequence. So one person should be looking at that randomization schedule and assigning who gets what. The product should all look the same, whether it's treatment or control, and nobody in that study except usually it's a pharmacist. Or the one person looking at that randomization schema, maybe 2 people, right? Everybody else should be concealed from that allocation schema. So they don't know if the next person coming in is going to get a treatment or control, okay? So then we also want blinding of the participants and the personnel, okay? Again, if you're randomizing, you don't want the people to know which group they're in, and the patients or the people that are in the study, and you don't want all the clinicians and people working with the patients to know. That'll give you a bias, okay? Then there's a detection bias. You want to make sure that we describe all the measures used to blind the outcome assessors from knowledge of which intervention of a participant received. That would be me. A lot of times, you'll collect your study, you'll lock your database, you give it to me. I only know group A and group B. I don't know who's who. Okay, I don't want to know who's who because that might bias what I do in my analysis. Okay, so and then of course attrition bias. Did people drop out of the study? Why did they drop out of the study? Are you going to still keep them? Are you still going to keep that study even with some missing people? Reporting bias, of course, selective reporting is bad. You're only picking, you're cherry picking, what we call cherry picking. Oh, I'm just going to report my significant findings, right? You want to study that if they had non-significant, they at least mention it on some of their findings. And then other sources of bias, and I like this: bias due to problems not covered elsewhere in the table. You might think of some. Publication bias would be one, things like that. But yeah, so this is a nice one to use, and there's many more. There's a systematic review of bias assessment tools is in this article here, and like I said, I have a place where you can go at the end in the references. But it's actually a systematic review of the actual assessment tools. I think they looked at 18 of them or so. Okay, so you can look at that one here. Okay. All right, so again, it's better to have 2 reviewers than just 1, and it's even better to have a third in case reviewers 1 and 2 disagree, and it could happen. It will happen. Okay, so it looks like we have some questions here. Does the Cochrane library refer to the statistician? Yes, it does. W.G. Cochrane. There's a couple different Cochranes, but it refers to W.G. Cochrane. Yes. Would it be good to compute each study's statistical power even if they didn't provide it? When you're doing a meta-analysis, you're basically synthesizing all the studies together. So that's one of the things that meta-analysis helps with, is when if you do have small studies and combine a bunch of small studies into a big synthesis, it's going to allow more power. You could keep track of your power. There's nothing wrong with that. But with a systematic review and meta-analysis, typically power is not really a problem because you do have quite a few studies in there, but you could always keep track of that if you wanted to, because if you don't have enough power, you won't see the effect maybe that you were looking for. But a lot of times in a randomized control trial, the first thing you do is check what sample size you're going to need, and to do that you need an effect size. So you're going into your study saying, this is the effect size I'm looking for, right? I want a mean difference of 10 points. That's what I want to see, that or better. right? That or larger. You can't see anything smaller. So if you come back and you have a mean difference of 8 points, it's going to show non-significant because you powered it for 10. But attrition can affect that. You might know. I always pad my studies by about 10% at least, 10, depending on how bad attrition is. Sometimes 20, maybe even more if necessary. But usually I always put 10% on, because especially the longer they are, people drop out for any number of reasons. And there's a lot of reasons you can't in a randomized trial. Non-compliance, you didn't take your medicine on time, all kinds of things. Just don't show up. But yeah, so these are things to help you keep things neat and tidy. And let me see if I have any more questions. Oh, let's see. Will there be the same number of studies in the systematic review as in the meta-analysis, or can you have more studies in the systematic review and only a subset in the meta-analysis? Or are there guidelines in minimum versus maximum number for inclusion? Okay. You typically, when you do a systematic, it depends on your systematic review. Sometimes you can do a systematic review without a meta-analysis, right? But if I'm going to do a systematic review with a meta-analysis, I'm going to have both. You also can, we're not going to cover it today, but there are subgroups analysis. So where you will take maybe that big bunch of systematic review that you have, and you might divide it up into smaller groups. There's also something called sensitivity analysis, where you might pull out one study, or you might pull out a couple studies and see if you still get the same treatment effects. So you can play with it that way, yes. But typically, overall, first you're going to include studies that are just even going to make the cut. Then you'll probably do a meta-analysis on those, and then you'll go into your subgroup and your sensitivity analyses if you want to dig a little differently, just to check to see if the treatments change or stay the same. There's also something called meta-regression that we're not going to go in today, but that also helps. You can throw things like gender and confounders, maybe, age groups, things like that, or even age itself in there, and basically do a regression meta-analysis. And that's sometimes something you can do also instead of all the little sensitivity and subgroups analyses. So, bias assessment tools. Okay, most bias assessment tools will include these items below, and as I already showed you, we saw it on the Cochrane, right? Those allocation, concealment, randomization, comparability between the groups at baseline, very important. Randomization should take care of that. But some studies will still do baseline. I still like to do baseline measurements because you never know. You can't. It's all about probability. Nothing's 100%. So that's why you have that 5% chance of error, and you have that p-value of 0.05. You're allowing yourself to be wrong or off 5% of the time. Hey, it doesn't hurt to check baseline, and cross your fingers you don't have any significant differences, right? And then of course, was everybody compliant and adhered to the study correctly? Because that will matter. And of course, a percentage of participation or attrition, also will matter. So we looked at all that already. But again, as you see, most of those goes with randomized control trials. So there's another thing you can remember called RAMBOMAN. About bias assessment tools. So you're going to assess degree of bias or the random error, non-random error. We always have random error. Bias is non-random. It's something that's introduced, something that we did, or something that the studies did, or it's not something that's just random. Okay. So this acronym RAMBOMAN is going to help remind you of the main causes of bias in a study. So bias can occur when participants are being recruited, which is your R, or when participants are being allocated, which is your A, right? Or to the exposure comparison groups, right? Your treatment or control. In studies that require follow-up, bias can also occur if participants are not maintained in the groups they were initially allocated to, which is your M. We also want to make sure that we have blind or objective measurement, which is BOM. You want to make sure that everybody's blinded and that nobody knew who was in what group, and the patients didn't know which group they were in, right? And then finally, the AN is the AN of the RAMBOMAN refers to bias introduced at the analysis stage of a study. For example, we don't undertake intention to treat analysis on, we maybe intention to treat means that everybody that came in the study, you have to include whether or not they completed it. Okay, so maybe we do some other type of, we take out some people for, you know, they didn't follow, we didn't have, they were lost to follow up. Well, we should still include what we have. Okay, so that's a whole other area to talk about. You can do it, but you have to say in your protocol what you're going to do. Okay, or if you don't adjust for confounders in the analysis, there could be something causing that treatment effect that wasn't even what you studied. Okay, another question I get is, should we include or exclude low quality studies? And that's a good question. So you want to consider the findings of all the studies have error, right? All studies have errors. All studies have limitations. It's being too restrictive could restrict your ability to generalize. Okay, if you're doing a synthesis of a literature, but you're only taking a little piece of that literature to synthesize, then maybe you're being too restrictive. You want to be able to include as much as you can, really. Being too inclusive might weaken the confidence that can be placed in those findings, basically. Okay, and methodological quality, again, it's subjective. It's often in the eye of the beholder. Okay, so you have to do your best to strike a balance that's appropriate to your research question. Okay, and also, include it in your inclusion criteria and your exclusion. There might be certain studies that you will exclude. Joe Smith's opinion. Well, who's Joe Smith? Things like that. So, or maybe if a study you look at one and it doesn't really have all the details you're looking for, and you're not sure of it, well, then you don't know if you're comparing apples to apples. You might want to exclude that one, even though it might have been nice to include. So, yeah, it's kind of heartbreaking because they become like your little babies, and then you've got to cut some of them from the team. Yeah. So let's see if we have any more questions on systematic review. Oh, what's the M again? It's I think it was the 3 BOM, blind or objective measurement. So blind or objective measurement. Okay, so that means you want to be blinding. So yeah, that gets three letters. Let's see, what other questions do we have? Oh, what's the first M? First M. Maintained. Participants are in studies that require follow-up bias can also occur if participants are not maintained in the groups they were. If you've changed a person from one group to another group, like a crossover study, but a crossover study, you're changing everybody, right? Everybody gets a chance to be in all groups. But it could be bias. There's definitely going to be bias if first they started in a placebo and somehow ended up in the treatment, right? So, yes. Let's go on to meta-analysis. Okay. So basically, the systematic review part of this is going to be the most time consuming. You're going to look at what I show you in MedCalc and you're going to say, that's it. But it's all this work up front that takes the most time. And a meta-analysis is better in many ways than just one study that you're doing a null hypothesis test in, right? Like I have a randomized control trial. That's great. That's our best type of individual study we want. But meta-analysis is usually better because you're taking many studies and hopefully as many randomized control studies as you can that meet your qualifications. And so it's going to make it a stronger, right? Null hypothesis statistical testing is very dependent on your sample size. We talked about power already a couple times. I also have a little webinar on the YouTube channel that talks about power and sample size. The bigger your sample size, the smaller effects you'll see as significant. Okay, so if you don't have a large enough sample size, you might have a huge effect. You might have a great big effect where it's like, obviously the treatment was great. Look at how well these people are doing. The effect was wonderful. But you didn't have enough people in the study. Okay. Typically, if you have a huge effect, you don't need a lot of people in a study. But it's very dependent on the sample size. The bigger your sample is, the more you'll see the littler effects. The smaller your sample, the more you're going to miss big effects because you won't have enough power. So null findings in a null hypothesis statistical test don't have the same importance or weight as a non-significant finding. And again, it's because, I guess I should have said a non-significant finding in a meta-analysis because null findings are non-significant. So I should change that slide. Let me see what slide that is, slide 20. Yeah, so when we do meta-analysis, we weight. Typically, a weight that's used quite a bit is called the inverse variance. You just take the variance that you got, which I will show you where you can go and get that. You take the variance and you just take the divided by the variance. That's your inverse variance, and that's how you weight the studies. Sometimes sample size will be weighted. In the larger sample sizes are going to be bigger studies are going to be worth more than smaller studies, things like that. So non-significance might it's not the same as a non-significance in one study means, oh darn, non-significant. But non-significance in a meta-analysis, it doesn't really mean the same. It's part of a bigger whole, is what I'm trying to say. Meta-analysis combines many similar studies with the focus on the magnitude and direction of the effect, and that's called the effect size, and that's what we care about. The effect size is not about significant or not significant. It's about how small or large of a difference, correlation, change, whatever was noted. And which direction did that finding favor, right? Was it favoring treatment or control? So you're looking for the treatment effect, basically. You're not looking at whether it was significant or not. You're looking at what was the actual effect. And you can do that in an individual study too. But for a meta-analysis, we want to look at what's the overall effect of the literature we have, of everything we have that we could find that was usable. So there's so many effect sizes, okay? I like to think of the effect size as the dependent variable, or the outcome. It's going to be the outcome of the combination of the studies. The effect size obtained, it's obtained from a combination of the standardized findings across all the studies. So you want to standardize your findings, right? You want to make them all kind of, meet a standardization, right? So that you can compare your apples to apples. The findings, apples to apples. You have to be able to compare all the studies similarly. Okay, so there are so many types. We have effect sizes based on the means. So you have your raw mean difference, which would be unstandardized. You're just looking at just the mean difference. Okay. However, a lot of times, especially my psychological studies I work on, they'll use a tool maybe for depression. There are so many tools out there for depression. They're all scored differently. You can't compare them until you standardize them, right? So something, a raw mean difference is great if it's every study used the same tool, the same measurement. Maybe they were looking at blood pressure, and they had a treatment control. Okay, blood pressure is going to be the same, I mean, it's on the same metric for everybody, basically. It's, but there's not different scales for different people and different studies. So then we have the standardized mean difference, which is used quite a bit with continuous data, okay? So these are your continuous data ones. And I would say, I don't think I've ever used a raw mean difference. I've always used standardized on these. Then we have based on binary outcomes. So, I should say that these will be independent groups. Usually the raw mean difference will be based on independent groups. Standardized mean difference can be matched groups or pre-post tests. You'll see this a lot, okay? Binary outcomes, and they can also be used on independent groups too. And I guess, they both could be used on pre and post. As I'm thinking, as I'm talking here, well, wait, they could be both, okay? You have them based on binary outcomes, yes, no, go, no, go, right? Either or kind of thing. So you'll have your risk ratio, and that's based on studies, of course, with independent groups. Odds ratios are based on studies with independent groups. Risk difference can be based on studies also with independent groups. Then we also have correlations. And correlations are just associations. And that's basically based on study with one group. And maybe you're comparing a correlation of, maybe age with the outcome of some tool, or maybe the outcome of one tool, or, the outcome of depression with happiness or something like that, and so you're looking at a correlation coefficient. Okay, so there are different effect sizes. So then you look at all these studies and go, oh my gosh, what am I going to use for an effect size? So here's a very cool effect size calculator, okay? And you can go to Cytometrica with the C, not the K, and right here, you can just type that into your browser. It's a beautiful thing, but you can go in and let's see if I can just show it to you real quick. This is so nice. So it tells you a little bit about it here, computation of effect sizes. But you can have comparison of groups with equal size. That's Cohen's D. These are your standardized mean difference, your Cohen's D or your glass right here. Okay, and then you just put in what you have. Group 1, Group 2, standard deviation. You're going to do this for each study. Okay, so your study 1, what's the mean of Group 1? That might be, always keep Group 1 either treatment or control, right? Don't switch them up. If Group 1's treatment, it's always treatment. Group 2's control, they're always control. So you just put your means in, your standard deviations, and it'll give you your effect sizes. Okay, you put in your N down here of your observations. It's going to give you a confidence coefficient you'll pick. You'll usually pick 95%, and it'll also give you a confidence interval, right? So that's nice. So if you just say, like, I have a mean is 36.5 and control was 30, and my standard deviation was 2 in each group, and my sample size in both groups was 50. Okay, so there we go. There's our effect size. Okay, it's negative here. Because it says the mean in Group 1 was 36, it looks like it did some subtracting, Group 2 from 1. So that's the other way. How are you going to set it up? So you want to set it up to have your effect sizes go a certain way. And then here's your 95% confidence interval. Okay, and these actually are both the same. Okay, but here's good with different sample sizes. Okay, so if you have different sample sizes, which you almost always do, you'll put in your different sample sizes. Okay, and then it gives you some little notes here, repeated measures designs, more information. So this is a great little calculator. Okay, and as you can see, it goes all the way down. Here's your correlations, here's odds ratios, right? Pooled standard deviations, Kruskal-Wallis test. My gosh, you got all kinds. So very, very nice little thing. So I wanted to show that to you. So we're not going to go through and do a bunch of those today. I want you to let you know that's a nice place you can go. A long time ago, we had to search the literature and use Excel and calculators and just figure them all out. But and I still have to do that sometimes. Like sometimes that calculator might not have what you need, right? So you're going to have to do some more searching. Okay. So let's look at the difference between fixed and random effects models. Okay. Choosing between fixed and random effects models. All right. If there's very little variation between trials, then we're going to have a statistic to call it's called the I-squared. It's the like an information index. It's an inconsistency index is what it is. It's I for inconsistency. It's going to be low. Okay. It's actually the percent of disagreement or percent that it's inconsistent. So if there's very little variation between all your trials, then you're going to have this low I-squared, which we'll look at in a minute. And the fixed effects model might be appropriate. Now, with fixed effects, all studies that you're trying to examine as a whole are considered to have been conducted under similar conditions with similar subjects. So in other words, the only difference between studies is their power to detect that outcome. Okay. There's an alternative approach called the random effects that allows the study outcomes to vary in a normal distribution between studies. So it allows them to be different from each other, right? So many investigators consider the random effects approach to be a more natural choice than fixed effects. I certainly do, and a lot of it in medical trials, a lot of people do. More data are required for random effects models to achieve the same statistical power as a fixed effect models, and there's no exact way to handle studies with small numbers when assuming random effects. There's no exact way. So this should not be a problem with most meta-analyses, though, because if you have a meta-analysis and you have enough of the analysis, you should be fine. However, I would not use random effects models with the sparse data sets unless you have some expert advice from a statistician, because there are some little things that we might need to do to adjust the power on that. Most softwares will give you both fixed and randoms, and what I'm showing today will show us both. I almost always go with random. The way I like to do is think of it this way. If it's fixed effects, the outcome represents the effect for the set of studies I included in a meta-analysis, and that's it, just them. Okay, because we're assuming all the error is the same. Okay, once there, or the effect, all the effect is basically, it's the same underlying effect. Okay, under all the studies, and so like everything will be kind of similar. We're assuming that, but that's not true. All the studies look different. And that's why we're doing a meta-analysis, right? We're checking because we're getting inconsistency. Some are saying there's an effect, some are saying there's not, right? So I'll use random effects. And the nice thing about random effects too is the outcome is going to represent the effect for the population. So I can apply it to studies I didn't include. I can basically apply it to that phenomenon I'm studying. So it's basically not just the studies I have, but I could say, if you wear slippers, you won't stub your toes this percent of the time as if you don't. And I can pretty much say that's in general. And that's a nice thing to do with random effects. A lot of people will look at random effects first, and if it's significant, then they'll go ahead with their fixed effects. But sometimes you will get random effects and fixed effects. One will be significant and one won't. Then you're going to be basically stuck, with your random effects and non-significance, because you can't. You got to make sure that your random effects are okay before you go to the fixed, basically. But you can pick either, but say first what you're going to do. Okay. Random effects are going to make it harder, is what I'm saying. But if that's what you need, that's what you should use. Okay, so next thing you'd want to do is crunch some numbers. So there's many softwares and applications available to run these. I'm going to show you the demonstration in MedCalc. It's probably going to take me 3 minutes. Okay, but you can try RevMan. This is from Cochrane. Okay, and it's free, and a lot of people use RevMan. You'll read a lot of articles, they'll use RevMan. MedCalc, it costs money, but I have it, and it's fairly simple to use. R is always free, right? It's open source. They have the Meta package. I think they have a Meta Reg package too. I think they probably have a lot of Meta packages, but it's free. You can check it out here, and here is a nice reference for performing meta-analysis in R also, that you can put into your browser and check. SPSS, I don't think it necessarily has anything for meta-analysis in it, built in, but David Wilson has a macro that you can use to compute a meta-regression and other regressions, and it's here, okay? Stata, you can try this. This is from UCLA, one of my favorite websites, the IDRE website, okay? And they have an introduction to meta-analysis in Stata. And Excel is free, okay? There's an add-on. And I have a blog I wrote, oh gosh, maybe about a year ago. And it was when I had this one really strange study, the one I was talking about with all the different effects and everything. And I had subgroups that I wanted to analyze. There's this add-on you can get for Excel. It's called Meta Easy, okay? And you can go to my blog, and there's information, there's links, there's even a little data set. I think I use superheroes. So it's a little fun data set, so you can play with that. But it's great. I love Meta Easy. But those are some of the softwares. Okay, so here's some more terminology. Now these are things that we're going to need to use for our meta-analysis. Q is Cochrane's Q. Yes, it's named for that statistician. And it's a test of heterogeneity. Okay, so it's going to examine a null hypothesis that all the studies are evaluating the same effect, right? And that any variations are chance occurrences. Okay, so it's not useful when the number of studies are small due to low power. There's another one that people came up with later. I can't remember who came up with this one, but I squared is a inconsistency index. Okay, it quantifies the effect of heterogeneity by measuring degree of inconsistency in study results. Okay, it's the percentage of total variation across the studies that's due to this heterogeneity, these differences, rather than chance, because there's always chance, but it's actually looking at the total variation that's due to, wow, there's inconsistency of the studies. Okay, the values are between 0 and 100, so you're going to set things that you might get as negative, then make it 0. Okay, so if you have 0, that's no heterogeneity. If you're between 0 and 25%, it's low. If it's 25 to 75%, it's moderate, and of course 75% or more is high. Okay, so we'll be checking those when we run our model. Okay, before we run the model, I'll show you these, because when I run it, you're not going to go, what's that? You'll see what it is. Okay, this is a forest plot. And it's a graphical representation of a meta-analysis, okay? Here would be all the studies we did, okay? And then here would be the different, what we found here was maybe it was this, oh, here we have odds ratios. Okay, this one was done with odds ratios. And here's all our studies, okay? So we just go down here, this 1 in an odds ratio, 1 means that there's no difference, that the treatment control, there's no difference between the groups. This side over here is going to favor your control, and this side of the one over here is going to favor your treatment, okay? So what you want are these odds ratios lower than 1 to favor your treatment. And as you can see, most of the studies do. We do have some studies here that also, but although that do, they have, they favor the control. The bigger squares mean the studies were bigger sample sizes, okay? And then you have these two little things down here. You have a fixed effects and a random effects. And this is just showing you the overall effect size for all the studies combined. They almost touched the 1 on this one. So they're significant. And it looks like they favor the treatment. So that's good. And then we'll get some printout that explains this a little bit more. Okay, and these are basically your confidence limits for each of your studies. Funnel plots. Okay, this is going to be used to assess bias. Okay, I talked about some bias, prominent causes of bias or publication bias, with studies giving positive results more frequently submitted for publication, more likely to be published. Larger studies published even if the results weren't positive because the researchers want to see something in writing for all the work they did. English language bias. Negative studies are less likely to be published in English journals. That's typically true. English journals aren't going to pick it up if they're not significant. Okay. There's studies with positive conclusions are cited more frequently and thus are more easily identified and incorporated in a database. The bias of assessing, the basis of assessing bias is that if all of the studies give random assessments of the same unbiased mean value, the plot should be symmetrical. Okay, so these dots should all be, you should have equals on each side. Okay, equal number of dots, and there should not be any holes. Typically what you'll do is you'll have a big hole down here in the bottom somewhere. Okay, here we have some, so it looks pretty good. Okay, up here I see this, and we'll look at it a little bit later because this is the same thing I'm going to run. But this guy's outside of our little funnel, but I'll tell you in a minute why I won't worry too much about him. Okay, but what you want is kind of symmetry, equal number of studies, and you kind of want them without any kind of patchies. Okay, typically the holes will be down here. Okay, so I'm going to try to bring up MedCalc. And I'm going to try to run one of these. And so let me see if we have any questions. Do we have any questions before we go? Are there guidelines on the minimum or maximum number of studies to include in systematic reviews or meta-analysis? Now it's asked by Leslie. No, there's not. I would say I wouldn't bother doing one unless I could put at least 10 in. I've seen them done on lower. I've seen them done on, higher. I think the most I've done, I did one once on 50 or so. I think the one I'm going to show you today is 50 or so. I often do them with that many, but I mean, you can have 100. Typically, once you're done with the inclusion and exclusion criteria, I don't think you'll hardly ever go over, if you go above 100, I think you're really overdoing it. And if you go, of course, lower than 10, then it might be why bother. But no, there's no real set ones. Again, Leslie, like I was saying, most of this stuff is subjective. And so it's basically, and the reason it's subjective because there's different types of research. This covers all types of research, right? You do this type of analysis, meta-analysis for anything, any type of research out there. So there might be different rules in different research areas, okay? I have another one here. How do journals usually classify meta-analysis? As a review article? No, they will include it as an actual analysis. It will be, basically a study, a published study. So yeah, they will publish the whole thing. Okay, good. All right, so let's go ahead and try this in MedCalc. So I'm going to pull up my data. Okay, so basically I used a bunch of colors and stuff and just kind of made this up a little bit to use. But anyway, so what we'll do, we're going to go into, open up our MedCalc. Here's our data. We put it all in. Okay, we have here our studies. Okay, we have our intervention, how many events, the total, and the control events, and how many there were in the control group, and then how long we followed up. Okay, so on this one, I don't think we'll really need a follow-up time. I'm just going to do this, that we're going to pretend that we stubbed our toes. Okay, we stub our toes a lot, but we're thinking if we wear slippers, because I know if I wear slippers, even if I stub my toe, I don't have an injury. So maybe we should do something like that. If we wear slippers and we stub our toes, how often do we hurt ourselves? Okay, so each event would be a time that we got hurt. Okay, and so our intervention group are going to be the people who wore slippers, and the control group are going to be the people who were barefoot. Okay, so we want to see if you're less likely, less likely to hurt yourself if you're wearing your slippers and you stub your toe. Okay, so we go into statistics. We're going to go into meta-analysis. And here it lets you pick, what do you have? A continuous measure, correlation, proportion, all these different things. I'm going to go with odds ratio. Okay, so here's our studies. I'm just going to click study because that's our group of studies. Okay, and then number of cases I'm going to put in. This is for the intervention groups. So intervention event, and oh, I'm sorry, intervention total. That's our number of cases. Now, the positive outcome, in this case, it would be negative outcome, but it's just of an outcome, okay? So intervention event, we'll go there. And control group, number of cases, we're gonna have here, and then events, okay? I don't have any filter I'm worrying about. And I have all this checked because I kind of want to see everything. And I'm going to pick my random effect. It'll give me both, but I'm going to pick that. I hit OK, and it does its little thing, and boom, there we go. It'll give us a little output here. Let's look at this first, if I can make this bigger. Okay. Okay, so it tells me my intervention group and what columns I use for what. Okay, here's our studies. I forgot to change some names up here, but I tried to make them all colors down here. But okay, so here's our intervention. Here's the controls, and here's the odds ratio for each group. It computed it for me. Isn't that nice? I didn't have to do it myself. That's what's nice about software. It even gives me a 95% confidence interval for my odds ratio. Okay, Z and P aren't in here. They'll be down near the bottom. And here's the weight it gave the study. If it was fixed and random, in this case, it gave them both the same weights. Okay, which is nice. I don't know why it did that. It might have been the way it weighted it. And softwares are different, so your software might give other information, okay? But then we're going to go down here. We can see all these different ones. As you see, the studies that had no events did not get included. They were excluded. But we included them in our systematic review. We liked them. We wanted to include them. They were important, but they did not get included in the meta-analysis. Sometimes people, what they will do is put a 0.5 or something like that for an event. A little ambiguous on that, but some people will. Just say what you did, okay? And then down here, and that way you'll include the studies because you'll have at least one event in one of the groups, okay? But I would say if they both had 0, I'd give them both 0.5, not just one. Don't bias it. All right, so here's our total fixed effects. Okay, so here's our totals for both groups. We seem to stub our toes 100 out of this many times and hurt ourselves in the intervention. And in the control, we hurt ourselves 130 times out of this many times of stubbing, okay, for all those stub toes. And here's our odds ratios. And actually, both the fixed and the random effects were both significant. And so they're both good, Here I will go with if I say the random effects model, then the odds ratio of 0.751 is less than 1. That means it favors the treatment. So 1 minus 0.75. That means when you have this odds ratio, you take it, and if it's lower than 1, you subtract it from 1, and that's your answer about how less likely you are to stub your toe. So you're about 25% less likely to hurt yourself when you stub your toe and you're wearing slippers. Okay. Down here we have our Q statistic, which is for the heterogeneity, and it gives us a p-value right here. We do not want it to be significant, and it's not. So that's good. These numbers really are kind of meaningless, really. You have your number of studies that were looked at and then the Q, you can look up the formulas and see, but what you really care about here is this p-value on it. Okay, the inconsistency index, wow, is 0. Okay, confidence interval though was from 0. It could have been up to about 39% of the effect was due to something in the studies, but we got 0 for a point estimate, and it could be 0. So we're happy with this. And we're happy with this, and we're happy that slippers help us. And so then we would next need to write all this up, okay? But let's look at that's the data. Let's look at the funnel plot. Okay, as I was saying, there's this one study right here, and I don't think it's going to tell me what study it is it? Scarlet. See, I named them all colors. Scarlet Seattle. This is funny. My granddaughter Scarlet. That's why I was naming them colors. So I gave one of them Scarlet. So we might want to go back and look at Scarlet. and see what happened here. It looks like, because right down here, now sometimes you'll get different kinds of funnel plots. This one has the odds ratio down here and the standard error up here. Sometimes you'll get different numbers up here, okay, on the y-axis. Also notice this. Here we're going from low to high, right? But here we're going from low to high down. So here's our standard errors are bigger down here at the bottom, okay? So when we look at this funnel plot here, I guess it's not going to let me write on it, but here's my arrow down here, okay? So down here, what we have, for instance, here we had a good effect, a good treatment effect, and we also had a very nice, it's a very large standard error. So I'm assuming here that probably we didn't have a very large sample size. I'm assuming if we look at Scarlett, first of all, she had it had a negative. It went the other way. Okay, their study showed that you were better off barefoot. It looks like, and also since we have the standard error up here is rather small, it was probably a rather large sample size. So let's go back in and see if we can see if I can find my med count. Come back up here. Okay, there's Scarlett. Here's Scarlett. Okay, 358 in the treatment group and 356 in the control group. Actually, the intervention had 18. So in the treatment group with the slippers, we had 18 events that were owies, and for the control, only 9. Okay, so that's kind of what that's telling you. So that's kind of weird, but hey, it matched the criteria. We're keeping it in. Okay, and I wouldn't worry too much about one study. Okay, but that was a big study that went the other way. And what we're doing is synthesizing the literature, not just the good stuff, right? So we want to make sure we keep that. Okay, and okay, so we looked at that. Do we have any questions? Let's see before we go into some of these final things. We do have a couple. Random effects again. Okay, we'll look at that. We'll look at that in a minute. So let me go ahead and finish this, and then I'll answer some questions because we're almost done here. Registration and publishing. Okay, so here's what you would do for Cochrane Review. Here's a little place down at the bottom where you can go and look this up. They also have something now called a living systematic review. Instead of going back every couple years to update your review, it's ongoing. That's new to me. I haven't heard too much about it. I want to look into it myself. I learned quite a bit putting this together, like, oh, living systematic review. So that's interesting. Okay, so Cochrane would probably be one most of us would use. There's also the Prospero. I don't know what Prospero stands for. I know it's a Greek god or something like that, but I don't know why they chose that. But Perspective Register of Systematic Reviews, and they're based in the UK. Okay, and here's some of the benefits. Okay, whether it's published or not, it's a nice permanent record. It's in there. Okay, and another thing, when you're reviewing a systematic review, there's another acronym called FAITH. Okay, so did the reviewers find the relevant studies? Did they appraise the studies for their validity and precision only, and not really like, oh, which ones I like or not, right? Did they include high quality studies? Did they total up the findings of individual studies? And what was the heterogeneity like? Were they sufficiently similar, right? So, so those are things we want to look at on those. What we didn't cover today: subgroups analysis, sensitivity analysis, and meta regression, but I did put some links in here. Okay, and again, you can break down these meta analyses into smaller groups if you want to look at a little differently. A lot of times in sensitivity, what we'll do is recently I had one where it's like we're going to look at different times of follow-up: 3 months, 6 months, 12 months, 1 year. Just to see if things changed over time. That happens quite a bit. Sensitivity, maybe maybe it worked good for people of all ages. It was this treatment, but I think it might work better in an older population. So maybe I only want to look at people that are over 40 or something like that. Okay. Here's some references. This is a lot of the seminal work. Okay, and then here's some more references. Okay, risk of bias assessment tool. There's a link to it. Another 5 things to know about meta-analysis. Love this blog. Okay, and here's that nifty effect size calculator. Okay, so those are right there. And oh, I guess I did not have the Q&A, so we'll just leave it on the final slide. And let's see, I'll stay a little bit longer and answer some questions. So let's see, and I have one here. Can you explain fixed effects and random effects again? What is the difference? Okay, it depends on what you're looking at, Jerry. But in general, if you have fixed effects, what that is saying is that whatever results you get, or whatever findings you're seeing, or whatever outcomes you get or your analysis shows, you can only apply that information to the actual people, records, studies, whatever you included in your analysis. Okay. Random effects means you can generalize that. It means that you basically, it's not including just what you included. There might be some other studies that could have been included that weren't. So it's more generalizable. Basically, you can take the information from a random effect study and say that it's more generalizable, that it's you basically took you might have taken a sample, but you're generalizing it back to the population. Okay. And effects, you took a sample, but you can only say those results apply to that sample. Okay. There are other types of fixed and random effects that are other meanings, but in general, that's the main meaning. Okay. Does MedCalc have a good help menu on this topic? Yeah, usually if you type in MedCalc and meta-analysis, it has a whole, you can find many pages on it. And it does. It basically walks you step by step through it. It also tells you how it handles zeros on odds ratios and risk ratios and stuff. Yeah, it's pretty good. And it costs, what did it cost me? I think it's like, you can get a trial version and try it out. Most softwares, you can get a trial version, right? You can get a trial version, try it out. But if you do them a lot, it's nice. Meta Easy, I like also, and it's free, and it's in Excel. The only problem with Excel, and statisticians don't like it too much, is that there's rounding error. So we have to be careful with Excel. But but I like the MedCalc for the meta-analyses. And yeah, they do. They have a very good help pages, and I think it costs about $600-700. It might have went up. That's when I bought it. Okay. You have any other questions? Okay, here's another one. Oh, 200? Oh, that's great. Okay, $200. Wow. Well, maybe I had to pay more because I'm corporate or something. What would be an example of a random effect, and does it require some guesswork to assume it's generalizable? You make the assumption up front. So it's not going to tell you, oh, you have random effects. So you're going to make that's one of the assumptions you're going to make up front. And as I was saying, most meta-analyses, I'm going to say I have a random effect. I could go into other studies and say, what's random effect or not. If you're doing, say, for like an ANOVA or something like that, maybe on crops, and you have all these different plots, and you have different representatives in different plots, but you're not going to look at every representative in every plot, right? So you'll pick a couple representatives out of this plot, a couple one out of that plot. You'll run your numbers, see if there's any differences. Okay, if you looked at every representative in every plot, then you could say you have fixed effects, basically, because you looked at everything and therefore everything's included. But otherwise, if you're looking at just the little bits of them, pieces of them, you're taking a random sample and you're assuming that anything that all the effects you got can be generalized back to all the little plots and all the little pieces of the plots. So that something like that would be an example, but and it is something you would say beforehand. But otherwise, this was fun for me. I thought it was interesting. It was a fun one to put together. So it doesn't look like I have any other questions, and we're running over a little bit. So we should have the handouts and the recording up in about a week or so. Thanksgiving's coming, so maybe give me a little leeway there, okay? A week or two, but I will follow up as soon as I can. As soon as I get the recording all cleaned up. As you know, staying here for the live event, we have a little bit of dead space we're going to have to take out. So thank you guys for all coming, and I hope you enjoyed it. And if you have any suggestions for the next one, it's going to be in February. I'm not sure yet what I'm doing, but I'm open to suggestions. And okay, have a great holiday, everybody. Okay, bye-bye.